Okay, let's talk about black body radiation in quantum mechanics. Black body radiation. So in black body radiation, it's it was the arise of quantum mechanics or quantum physics. So to illustrate what black body radiation is, we have to talk about something as perfect black body. Okay. Now, what is perfect black body is it is that if we have a certain a hole over here and it has an entrance to a body in which if light passes through it and gets absorbed, the energy and the energy of the energy gets absorbed, and the remaining energy is absorbed by the collisions. Remaining is absorbed by collisions. Okay. Now, through reflection, and the process through which it's absorbed is reflection. Now, after the energies have been absorbed through the hole, the narrow hole through which the light went through, emits all the wavelength uh, light, all the wavelengths of light. Okay. Now here, when we draw the graph of this experiment with the wavelength and intensity, which is light. Okay. Now intensity. Sorry. Now what this shows is that we have a curve which is like this, with many graphs like this, and like this. Now what these points are actually, they are known as maximum lambda. Okay. And this maximum lambda is like known through Wayne's law, and which is known as uh, this max equals 1 over temperature, meaning the more the temperature, the less maximum uh, wavelength. Means if we have our temperature, let's suppose if we decrease the term, it goes lower, or we say approach zero, what we observe is that this value is max infinite, or it's max value. But if we do the same for the opposite, increase the temperature, we see that it doesn't follow. It can't explain it. It can't explain. So this equation can express the the left part of the equation over here, this part, but can't explain the right part. It is only possible when temperature is approaches zero, we get maximum values of lambda, and these are different values of temperature. Okay, now then what happens is, if this equation is for the left side, we have one more equation which is for the opposite side, which is known as energy density equals, this is temperature by the way, equals 8 pi frequency square over c cube kt. This is our second equation, which shows, which explains explain the right side, right hand side. Okay, only applicable for right side with more lambda. So this part over here is for the lower lambda, and this part is for a higher lambda. Because we can see, right, the wavelength increases on this side and decreases on this side. So this part is for this, and this is for this second equation, which is known as violin. I think it's like this, violin, something like that. I will not spell it. Equation. Now, but then comes Max Planck. What he did is that he solved this catastrophe. I'll tell you what this catastrophe is all about. He solved this catastrophe though with his assumed that he assumed this equation over here. He assumed that. He assumed energy depends on frequency. On this single assumption became the rise of became the reason we have quantum physics. This single assumption caused us to have quantum physics. Now, what's the equation telling us? What is the use of this equation? This says that energy is discrete. Now, what is discrete? Discrete means it comes in small packets. This. These are all small packets, individual small packets. But when we talk about continuous energy, it's like this. We talk about, look, the energy is spread all over wave, all over wave. And that's not allowed in quantum mechanics. Energy is discrete. In quantum mechanics, we have discrete energy. So here we can say E equals h lambda, h frequency, and E equals to Boltzmann constant T. This K is known as Boltzmann constant. Now, what this equation shows that here temperature is the variable, is a changing variable. It's a thermal energy. And this thermal energy shows continuous change in energy. Continuous change. Whereas this frequency over here shows discrete change. So what Einstein, or the sorry, not Einstein, Max Planck. Einstein was also one who has some contribution to this. So what Max Planck did is he changed kT with something known as hv over E of hv over kT minus 1. Now, by applying this, putting this equation instead of this kT, look what we get. We get energy density equals 8 pi v cube as the frequency cube h over c square 1 over e of hv over kt minus 1. This is our final equation. And this equation removes the ultraviolet catastrophe. Catastrophe. Now, what is this catastrophe? This catastrophe is that when we have energy as kT in our energy density, we get the followings. The followings are shows increase of energy density when there is increase of in frequency indefinitely. So when we have this as our energy, that's what we get. It shows that the energy keeps on increasing without any limit. That's one point. Second point is that it predicts that um, it predicts that the energy has infinite value. It doesn't change in the ultraviolet region. That's what's called ultraviolet catastrophe. In the ultraviolet region, the energy goes to maximum, infinite, which is wrong according to the experiments. Experiments show that at certain level, at this level over here, after this point, the energy starts decreasing. Black body radiation is at peak. Then down the slide, decrease. Okay. Now, what experiment shows is they have down increase. They don't. It doesn't go infinite. It decreases according to after a certain amount of frequency. Now, this was solved by Max Planck by what he added energy as discrete values known as quantization of light. Quantization of light. Now, what is quantization of light? It was actually after the black body radiation. Max Planck assuming that light works as individuals. Max Einstein made improved his photoelectric effect, showing that energy comes in discrete packets. Energy comes in discrete packets or units. So how he explained his photoelectric effect using it, and let me illustrate what his photoelectric effect shows. It shows photons, individual photons comes in, hits each electron in the metal, and on collision photons cease to exist and electron bounces off with k dot e max. And okay, what if I do the same experiment with wave theory? Now, What's interesting here? Wave theory, in wave, energy is spread, as we talked earlier. Energy is spread. Energy is spread. Now, in photon, we know that the emission of electron is instantaneous. How do we know that? Through experiments. Okay. Now, why does so that's why energy is spread, and by energy spread means we know that if energy spread, for it would take a lot of time for electron to be released if this energy is given to this electron, right? Time delay. That's one more factor which goes along with the energy spread. Energy is distributed all over the wave, which shows that it would take a lot of time for energy to be transferred to the electron, we're causing time delay. That means there would be a lot of time before the electron could be released, which is not possible because of experiments showing that electrons are released instantly. So wave, that's the reason wave theory doesn't apply to uh, photoelectric effect. Only the particle theory does. Particle theory. What are the factors of particle? What are the observations and what happens in particle theory is number one, photon hit or collide with electron. That's the first step. Second step, energy transfer of energy to electron. E is equal to hv. Okay. Second point. Then third, photon cease to exist and electron is emitted instantly. The moment they collide, the electron is released. That's the third point. Fourth point, on the condition that on the condition that the energy of light, that photon equals the work function, equal or greater, equal or greater. Okay, I'll just add this, equal or greater than the work function of metal. And then the other point is the remaining energy is used as kinetic energy. I think we all know that. And the reason for kinetic energy with max written shows that if we have an electron on the top, easy to remove, but the same electron at the bottom would require more energy. Okay, that's the reason we have max written, because after all that hurdles and after all that difficulty to resistance of the metal, electrons released, that after that the kinetic energy remaining is the max energy it has with because of its emission or bounce of out of metal. So and we also say that the photon must have minimum frequency. Minimum, no, not frequency, minimum threshold frequency. That is the minimum frequency, if I'm right. Yeah. So these are experiments of this is the particle nature of photoelectric effect, which it does follow, and the wave nature doesn't follow because of we having experimental evidences. That's why we for sure know that particle wave nature cannot be assumed in or cannot be used in a photoelectric effect. Assume means we don't know the experiments, but we do know the experiments, so we will not assume. We for sure know that. So the idea of photons existence is the reason we have photoelectric effect, and the reason for and the cause of that is Max Planck assuming that light is constant. It's not it's discrete, not continuous. Light is like this. It's not like this. So that's the reason we have quantum mechanics, and that's the reason we have what we have today. So it's known as quantization of energy by adding E equals h v, which is energy equal Max Planck is the constant which Max Planck came up with. So and yeah, that's it. Thank you.